Welcome everyone to our talk, introducing SubCrawl, which is a framework for analyzing and clustering hacking tools and payloads found in open directories. SubCrawl was designed and developed by myself, Josh, as well as Patrick and Alex, all of HP's threat research team. If you have any questions or feedback, please feel free to reach out to us at the provided email addresses or Twitter handles. As our presentation title suggests, the focus of our framework is on discovering open directories and then analyzing the content. So why open directories? Malware is often distributed through compromised web servers, and occasionally these servers are configured to show directory listings. These listings can provide a complete picture as to what is on the compromised host and how the malware is being distributed, as well as how the compromised host is being managed. Not only can open directories show what payloads have been uploaded, but also other tools such as proxy scripts, command and control panels, and even web shells. Finding and analyzing this information over a broad number of hosts can further lead to insights into how the hosts are being compromised and what threat actors share common tactics. In doing this research, we had two primary questions that we set out to answer. Do threat actors compromise websites themselves or by access to them? How are websites used for malware hosting and distribution compromised on a large scale? We'll set out to provide answer to these questions throughout the rest of this presentation. Before we jump into the data, let's talk a little about open directories and establish a baseline understanding of what we mean by an open directory. Simply put, an open directory provides a listing of files and directories on a web server. The screenshot to the left shows a common example of an open directory, listing both PHP files, which happen to be proxy scripts here, and DLLs, since this was an open directory for compromised hosts used to distribute malware. Most open directories also provide a link to the parent directory. When harvesting links from open directories, this is one way to begin to explore for new content towards the root of the web server. Not all open directories show the same information, but it is common to see properties such as timestamps, file sizes, and sometimes even descriptions. One of the many benefits from a research perspective when finding open directories is that it can allow for the downloading of files which may otherwise not be discovered, or would be interpreted by the web server. This often allows for a greater understanding as to the purpose of the compromised host by the threat actor. Open directory pages often begin with the string index of, in both the title of the page as well as in the content. This becomes a strong value to test for when determining if an HTTP response is an open directory, and at the core of how SubCrawl makes this determination. While the open directory will provide links to parent and child directories, SubCrawl also parses the initial URL, removing subdirectories until it reaches the root of the URL. These generated URLs are added to a scrape queue, and as the engine crawls sites, any newly discovered URLs are deduplicated before being added to this queue. This allows for a more thorough investigation of the host. Sometimes, from an open directory, the parent folder is not open, but below that, it may become open again. Next, we'll take a look at the SubCrawl framework. SubCrawl is a modular framework designed to find, scan, and analyze open directories. The framework consists of four primary components: input, storage, and processing modules, and then the core engine. SubCrawl has been written in Python 3 from the ground up and provides integrations with the URL house and PhishTank for input sources. But you can also provide your own input file that contains URLs to scrape. And to achieve long-term storage, analysis and data deduplication through MISP and SQLite. Now that you have an idea of what SubCrawl is designed for, let's take a deeper look at how it works. SubCrawl has two modes of operation, service mode and run once mode. In this diagram, we'll begin by exploring service mode architecture first. Service mode begins by processing input modules that help to gather URLs, and our current integrations include the URL house and PhishTank. Service mode runs these input modules periodically and adds them to a queuing system, which can then be picked up by the crawling engine. Upon initial loading, the crawling engine parses a YAML-based configuration file to determine such options as which modules to load, file extensions to skip scanning, file magics, and MISP integration options. As the engine is scraping URLs, if content is determined to be a file type, it is processed by all loaded processing modules, such as the YAR processing or payload processing modules. A batch size variable determines how often results are handed off to the storage modules, which are called when either no further URLs are left to scrape or the batch size is reached. In run once mode, the only difference is that input URLs are fed to the engine by a file. instead of by the service mode input modules. Now let's take a quick look at SubCrawl in action. For this demo, I'm going to show you Run Once mode, which is currently not set up to use the MISP or SQLite storage modules. For output, the console storage module works best. This really isn't a storage module in the sense that it does not store any data, but simply prints results to standard out. We felt this was an ideal setup for Run Once mode. First things first, let's grab some URLs from the URL house, using curl to query their API, JQ to select just the URLs, sed to remove those pesky double quotes from the filtered values, and then finally redirect this to the file that we'll use as input for Run Once mode operation. With our input files ready, our next step is to run SubCrawl. We'll use the -f argument to supply the path to the file, -p will define our processing modules, I'll use payload and Yara, -s defines the storage modules, and as we previously noted, we'll use the console storage module here. Now we're ready to start crawling. The engine will begin by loading the configuration file and any defined processing and payload modules. It then generates new URLs based on the input values, adds them to the queuing system, and begins scraping. For this demo, I trimmed our input source down to one URL that I know would provide a good demonstration. During crawling, the engine prints any matches that it finds. Here we have payloads in the PE files discovered, likely malware, and a Yara match for a password-protected web shell. When scraping finishes, the console storage module provides a summary of results. Had we used service mode, these results would have been added to MISP or an SQLite database. While payloads, that is malware that is intended to be executing on a victim system, are usually interesting finds, we also wanted to ensure that SubCrawl could help discover and identify a wider range of content. To achieve this, we implemented not only the Yara module, which of course can be used to detect far more than just web shells, but also the payload module to handle payloads of any type, ClaimAV to scan HTTP response content, JARM, which was developed by Salesforce and works by actively sending TLS client hello packets to a target TLS server, capturing specific attributes of the TLS server hello response, and then aggregating this in a way that creates the JARM fingerprint, SD hash for similarity matching, and TLSH for fuzzy matching. As you've seen, the processing modules are selected during runtime, and output from these modules is handed off to the storage modules during engine execution. The Yara module has provided us with the ability to not only identify such tools as web shells, but to track their use and reuse by threat actors across compromised web servers and campaigns. Now we're ready to explore SubCrawl service mode. We'll start with the built-in web UI and SQLite integration. We've wrapped this mode up into a Docker container and provided instructions to get started in the README on the GitHub project. It's quite simple though. You can clone the repository, then issue the command docker compose up build. Once the containers are up and running, you can open a browser to localhost port 8000, and you'll be presented with a dashboard that will provide a brief overview of scan results, such as scanned domains, scanned URLs, top tags, and top payload hashes. You can drill down deeper into this information using links on the left. Domains will give you a list of all of the domains scanned, plus a count of the actual URLs from each host. And URLs will, of course, provide a list of all of the URLs. This also provides insight into the HTTP status code, hash of the HTTP response, and the date it was scanned. Finally, there is a basic searchability to help you navigate your scan data a bit quicker. As you can see, this provides a more persistent crawling setup than the Run Once mode, but it is still limited in the data that is currently showing. To help address this, we also integrated with MISP. To use the MISP integration, you'll need to have a running instance of MISP and provide the necessary configuration information in the SubCrawl YAML, such as the host address and the API key. Showing the setup of MISP is really beyond the scope of this presentation, so I'm just going to jump right into our instance and show you some of how we've structured the data. With the MISP integration, one event is created per scan domain, and each event is enriched with tags from the URL house. These events were also used to track domains scanned and avoid rescanning if desired. I've selected an interesting host as it has been tagged by the URL house as Dridex, and we've discovered that it has an open directory with web shells. You'll also be able to observe related events, and this will help with future correlation activity. Inside each event, each scanned URL is combined into one MISP object with its attributes. For this work, we've created a new opendir object. The opendir object represents not only the URL scanned, but also the processing that was completed on them. In this example, you can see the hash of the payload delivery, as well as output from some of the processing modules, such as the Yara module, and that we have identified a protected web shell, meaning that it's a password-protected login. You can also see information like the TLSH hash, as well as other HTTP headers that were captured in the HTTP response. While there's quite a bit more that we could explore here, this was just to give you a brief understanding and insight into how SubCrawl works and how we began to structure the data. Now I'm going to turn it over to Patrick, and he's going to explore some of the more interesting findings that we've uncovered during our research.
Thank you, Josh, for this great overview and demonstration. And hello everyone, my name is Patrick. Now let's explore the data we collected and stored over the last few months in the MISP instance Josh just showed. The main objects I would like to focus on are web shell login pages we found on various websites. A lot of open directories, which were scanned and analyzed using SubCrawl, contained simple web shell logins, just like the one which can be seen in the image. The HTML code of the web shell logins are not always absolutely identical. The name of the input field as well as the value of the submit button sometimes vary. Some of the web shell logins try to stay undetected by showing a 404 error message to the visitor. An image of such a sample can be seen now. The user then needs to press Ctrl and the left mouse button, which triggers the JavaScript function to make the login visible. To further analyze those detected web shell logins, we wanted to create the correlation graph. MISP offers such a feature out of the box, which makes the analysis even quicker, as we have all the data already in the correct place. To make the correlation graph clearer, we created a reference event. This reference event contains all the hashes of the identified web shell logins with additional descriptions and screenshots. In the detail view of this reference event, we can now generate the correlation graph based on the SHA-256 hashes of the web shell logins. As a result, we can see 10 different clusters of similar but not entirely identical web shell logins. Connected to the center of each cluster, we can find all events containing such a login, and because we created one event per domain, we directly have this reference as well. Looking at the graph, we can see that 4 web shell logins seem to be very common, whereas the other 6 are not so much, and therefore only form small clusters. Another interesting anecdote is that some web servers hosted more than one variant of web shell login. The correlation graph we just saw formed different clusters by comparing the SHA-256 hashes. The integrated function in MISP can only generate graphs based on identical attributes. As we have only very small differences between lots of web shell logins, it would however be more interesting to form clusters based on the similarity, which is currently not supported. To still do such an analysis, we created a simple Python script which uses the trend micro locality sensitive hashing algorithm to calculate the similarity from clusters based on it. We already knew quite early in the data collection process that we wanted to do such an analysis, and therefore we calculated the similarity hash for all HTTP responses and stored them in MISP. The Python script therefore simply uses the MISP API to query the TLSH attributes and generate the correlation graph we can see on this slide. The result reveals 3 clusters. To get contextual information, we added the malware family, which was hosted on this particular domain, to each node in the graph. As can be seen, the 2 larger clusters are pretty much distinguished by the malware family and consists of simple HTML web shell logins. The 3rd cluster contains all observed malware families and represents web shells extended with JavaScript to hide itself. Here, just a simple table to give a few stats about the crawled websites, the amount of detected open directories, as well as the corresponding malware families. For Hensitter and Tridex, the percentage of detected open directories by crawled website is pretty high, with above 50% and more. Quackbot, on the other hand, is the malware family which was scanned the most, but only 5% of the websites formed an open directory. The reason for this is unclear, but maybe the threat actor distributing Quackbot is more careful in placing the malware on compromised websites than the other groups. Based on the results I just presented, let's try to form a conclusion and answer to the question if threat actors buy access to websites or compromise them on their own. Because we found the same web shell login distributed across various websites hosting Dridex, Quackbot, and Hensitter, one theory is that malware operators purchase access to compromised websites, maybe even from the same distributor. Having formed this conclusion, there is still an open question left. How are those websites compromised after all? Trying to answer this particular question, we looked at various characteristics of their websites. One potential infection vector we considered are vulnerable web server technologies and versions. Therefore, we evaluated the versions in use. We did the identification of the web server technology based on the HTTP response headers, which means that we sometimes didn't get the exact version and sometimes no web server information at all. A chart presenting the detected web server products can be seen on the image. As you can see, a broad set of web servers and versions seem to be used. Compromising such a wide range of web servers cannot be done by simply exploiting one or a few vulnerabilities, which means this attack vector does not really scale. Therefore, we suspect this is not the way how the web shell logins were deployed to websites. We did a similar evaluation for the used scripting technologies. As we also did this analysis based on the HTTP response headers, we did not get many results. A lot of websites did not disclose their used scripting technology or versions. As on the chart can be seen, we still got the information that various technologies are being used and also a number of different PHP versions. To figure out if this is a potential vector of compromise, we searched for common vulnerabilities. This, however, did not lead to any promising results. Similar as for the web server software, we suspect that exploiting vulnerabilities in the used scripting technology does most likely not lead to so many compromised websites, and therefore is not the way how the web shells were placed there. After looking at the used web server software and scripting technology, we decided to also have a look at the used content management system. We did not run a CMS detection scanner, but only looked at the URLs of the detected web shells. Using this very simple method, we found that around half of the websites had deployed WordPress. Only looking at those WordPress URLs, we noticed that most of the web shell login scripts were placed inside the plugin or theme directory. So, compromising such CMS extensions could also be a way to place web shells on websites. As there is again a large variety of plugins and themes, finding a common vulnerability is less plausible. Therefore, also exploiting CMS extension is rather unlikely in this case. At this time, we started to lose the hope of finding a way how those websites were compromised. Browsing through random open directories then led to an interesting clue. We noticed that the timestamp of the web shell login is the same as for all the other files in the same directory. Now, there are multiple possible reasons for that. Either it is wrongly displayed by the web server, the attacker modified the timestamp on purpose, which in my opinion would be a bit of an overkill for this use case, or the web shell login was placed there at the same time as all other files. By further browsing through even more open directories, we discovered a few other interesting things. At one point, we were able to download a PHP web shell due to a misconfiguration of the web server. The PHP file was not interpreted by the server, but served for download. The web shell consists of a simple PHP class which contains multiple functions as well as variables. So far, nothing suspicious. The class also contains two base64 string blocks and a few arrays which seem to represent PHP functions if the elements are concatenated in the correct order. Those arrays can be seen in the second image and resolved to functions like create functions, base64 decode, and string replace. Digging a bit deeper, we found the following. The first base64 block leads to the PHP code which can be seen in the image on the left. The resulting code is interpreted by the PHP function create function, which we saw in the array on the last slide. The executed PHP code is responsible for displaying a web shell login and handling login requests. The entered password in the web shell login is directly used to decrypt the second base64 string. If the decryption is successful, the code is also interpreted using create function. The decryption function can be seen on the second image. As we did not have the correct password, we were unfortunately not able to decrypt the second base64 string. We, however, think that this is most likely the PHP code of the web shell. Another interesting discovery was made by opening random JavaScript files in open directories. For various JavaScript files, we noticed that there was some strange looking code at the end, which was most likely appended. The image shows this JavaScript. Now, to me, this looks like obfuscated code, which should hide its true behavior. It makes a GET request to a defined URL and receives another JavaScript snippet, which is again interpreted. The domain of the GET request can be seen in the image on the second to last line. The return code simply sets a cookie called UTM-A, which is normally used by Google Analytics. The reason why this cookie is set, or what the purpose of the appended JavaScript code is not yet clear. I'm however pretty certain that the appended JavaScript code is not Google Analytics and put there by the attacker. To find more information about the appended script, we searched on GitHub using various keywords extracted from the code. The result was very interesting, as we found a lot of files containing similar appended code across various different repositories. Most of the results were plugins, themes, web frameworks, or entire websites which were uploaded. Let's quickly highlight one of the found repositories. The following image shows a repository containing a copy of the Laravel web application framework. The README file of the copy was absolutely identical, and the code very similar. Looking at the different files in the copied repository, we could find the modified JavaScript files, which are not present in the original repository. Digging deeper, we could even find a PHP web shell, like the one we saw earlier. Containing suspicious JavaScript and PHP web shell makes this repository look like a Trojanized version of the web application framework. Now, let's try to summarize the findings we gained so far. We noticed that the web shell login had the same timestamp as the other files in the open directory. And this was not only the case for one single open directory, but for many of them. Due to a misconfigured web server, we were able to download a PHP web shell, which we unfortunately could not entirely decrypt because of the missing password. Various JavaScript files hosted on the same domain contain suspicious looking code at the end. This obfuscated code makes a GET request to another URL and sets a cookie based on the returned result. Searching for keywords contained in the JavaScript code, we managed to find various GitHub repositories containing not only suspicious JavaScript, but also PHP web shells. And some of those repositories seem to be impersonating legitimate frameworks, themes, and plugins. Based on our findings, we came to the following conclusion, which tries to answer the question on how those websites were compromised after all. Our research shows that one way that web shells are deployed is by distributing Trojanized content management system plugins, themes, and software packages. Still, there seems to be an open question. What's the purpose of the JavaScript appendix? I don't have a clear answer to that, but I do have a speculation. Let's go through the following potential process together. First, CMS plugins, themes, and software packages are compromised or cloned by the threat actor. Then, an unsuspecting user installs one of those malicious packages on his new website. At this point, the website is set up and contains a PHP web shell. The threat actor, however, has no clue about this web shell yet and needs to get informed. If now someone browses to this new website, the JavaScript is executed and makes a GET request to the defined URL. The JavaScript therefore serves as notification mechanism for the threat actor. As this is a cross-origin request, the origin header is set, which gives the threat actor the indicator where the web shell was deployed. Finally, the threat actor just needs to test his new web shell and can then sell it for malware distribution. Now, this is just a speculation with a few open questions, and Trojanized software packages are most likely only one of many ways such websites are compromised. But it looks very interesting and also quite promising. And now, back to you, Josh, for the last few words.
Thank you, Patrick. It's now time to wrap up our presentation. SubCrawl is now open source and available on GitHub under an MIT license. We will continue to explore adding new modules for processing, storage, and input to broaden the framework's capabilities. We're looking for community involvement, so check out the tool and let us know what you think, if you run into any issues or have ideas as to how we can expand it. Crawling is a resource-intensive task, and we already have a number of ideas to improve crawling performance. So watch the repository as we start to roll out those new enhancements. One of our primary goals with developing this framework was to discover interesting data. And with the data that we've collected, we'll continue to look for interesting patterns in compromised sites. We also want to share with the community to help find ways to help mitigate these active campaigns and provide further integrations with platforms such as URL House, for example, by uploading new payloads that we've identified. Keep in mind that SubCrawl may already integrate with tools you're using. SubCrawl is ultimately just fed URLs, so if you have a source of URLs you are already generating, SubCrawl can scan them. SubCrawl also has the ability to save content. This could be useful for such use cases as archiving what you find or integrating into a sandbox workflow for further analysis and results. We want to thank you all for joining our talk. We hope you enjoyed it. If you have any questions, comments, or just want to say hi, please do so. We look forward to hearing from you. Have a great rest of your conference.